All right, good afternoon. So here we are yet again for yet another lovely session of ENGR 2302 Engineering Dynamics. All right, so let us begin. In the last lesson, we looked at the beginning material of Chapter 12 from the Bureau Mechanics book, and here we are going to continue on it with more of this again. So the basic idea here, or what we're going to look at today, our basic processes, we are going to work through a few example problems on some of the old material, looking at centripetal motion, radial motion, things like that, and other properties of force, momentum, etc. And then we're going to continue on some new topics, including some interesting things about orbits, etc., etc. And then next time, on Thursday's lesson, lesson number 6 or lecture number 6, we're going to start working with we're going to be looking at conservation, namely energy, work, potential energy, kinetic energy, the conservation of energy, and energy method for problems, and energy method problems. So let's work through some more examples here. Example. So I'm given the following task. Determine the rated speed of a highway curve, let me just go ahead and say a banked highway curve, with a radius of rho equals, or with a rho equals 400 feet, a radius of 400 feet, and an angle of theta equals, and a tilt angle, or a bank angle, and I will draw this out in case you can't visualize this, bank angle of theta equals 80 degrees. Equals 18 degrees, not 80 degrees, that would be quite extreme. 18 degrees. So in other words, what I'm showing here is I have something like this. Actually, let me just work through a solution. And I will draw out the free body diagram as part of the solution. So what's happening here is I have a banked curve. And if you've ever taken a look at a banked curve on a highway, you can see this here. It has an angle of 18 degrees. Well, this particular one has an angle of 18 degrees. A bank curve has an angle, a certain angle, and that angle lets a car travel around it without slipping off the curve. Now here, there would actually be quite a bit of outward grip. There would actually be quite a bit of grip on the between the car tires and the surface of the pavement. But for our purposes, let's just go ahead and assume that's zero. Let's see. What could we do if we were, how fast could we go around this curve if we were relying on only the banked curve to keep us moving in a circle? So if I were to go and, let me go draw the car out. I'm just going to draw the car as, well, a block. Because as we know, everything is a block if it's not rotating. And I'm going to draw an interesting axis. And I'm going to have my y-axis here, my vertical axis, but then I'm going to have my n pointing like this. My n-axis would be my center pointing, or my centripetal axis. So if I look at this from above, what's happening is I'm going to have some sort of, if I look at it here, there's this banked curve that's going around, and it wouldn't likely be a full circle, it would be only a part of a circle, and there is in order for this car to go in a circle, there needs to be some sort of centripetal force. And that centripetal force could be determined by, or could be produced by friction between the car tires, and it would have to be if the track was level. But in this case, the track is not level, so I'm going to assume that it is produced entirely via, essentially via normal force. So I'm going to have the weight coming down here. So if I draw if I draw my forces here, I'm going to have weight coming down here, the weight of the car. And notice I was not given any information about the weight of the car. So we'll have to see what kind of impact that has. But then I will have the normal force, Fn, the normal force or the reaction force, depending on what you want to call it. And so this would be the normal force, and this normal force is going to be perpendicular to the surface. So this would be 90 degrees here. This would be 90 degrees here. Now, what's interesting about this, the basic idea, or the fundamental idea of how this is going to work is, we're going to have weight acting down, and the component of the normal force that is vertical is going to have to counteract this weight. But then because the normal force is at an angle, some of that normal force will have a component that is horizontal, and that horizontal normal force is what will allow us to cause the car to move in a circle. Okay, let's work through that. So we have our free body diagram, and let's continue working. So in other words, if I were to draw this out, if I were to consider the car a point, let me simplify this a bit. If I were to consider the car a point, I would have normal force acting like this, F normal. I would have weight pushing down, weight pulling down, but this has to be equal to so this is my free body diagram. But what do we have to set this equal to? What are we setting our free body diagrams equal to? Remember what we called those? We called them inertial diagrams. Remember that? Inertial diagrams, where we show the acceleration that the system produces as an inertial force. So this is going to be equal to, in other words, these two vectors must come together to produce the following inertial force. And that's going to be simply M A sub n, which will in this case be equal to a centripetal force. And then if I label the vertical, label some angles, this is going to be this angle. If you work through the trig, you will find that this is at an angle of 18 degrees. This is at an angle of 18 degrees. So, so I have my free body diagrams and my inertial diagrams. That's step one. Step two, I'm going to resolve forces into components. Resolve forces into components. In other words, I could start by saying, all right, well, the sum of forces in the y direction is going to be equal to 0. So this means that F normal times the cosine of theta minus W equals 0, and then Fn must be equal to W over the cosine of theta. So I know that. That's good to know. But I'm not going to solve for this yet. I can't actually put numbers in yet, simply because I don't know the weight of this vehicle. I don't know its mass. I don't know its weight. So we'll have to keep working. And then the sum of forces in the normal direction, or sorry, in the n, yeah, we could call it the normal direction, or more, I think of it more as the centripetal direction, equals M A sub n, which is going to be equal to R. So we'll have R sine of phi. R sine of phi is going to be the, again, remember the normal axis, I drew it as pointing this way, positive. So this would be the n-axis and the y-axis like this. And so I'll have R sine, actually, no, sorry, not R, Fn sine phi, the normal force sine of theta, equals, now I need mass, but I've been working with weight, so I'm going to use W over G AN. However, I remember that centripetal acceleration has to be equal to V squared over rho, as we have seen previously, so I can put that in here. So I can get that essentially, now I know that Fn, however, is equal to W cosine theta, so I can, if I, so in the next line, I'm going to replace the normal force with W cosine theta and AN with V squared over rho. So I will get that W cosine theta, or sorry, W over cosine theta W over cosine theta times sine of theta will be equal to W over G times V squared over rho. All right, and so then if I work through this, the weight will cancel out. As we can clearly see, the weight will disappear. The weight will cancel out. And if I solve for V squared, or if I want to solve for vehicle speed next, I can get V. So I can, basically my whole goal, remember, was to find the rated speed. V squared is going to be equal to G rho times the tangent of theta. Times the tangent of theta. And then V equals the square root of G rho times the tan of theta. G rho times the tan of theta. And if I plugged in numbers into this, I would get that this is G, which is, let's say, 32.2 feet per second squared, times a radius of 400 feet, times tan of 18 degrees. And this would produce a final velocity V of 64.7 feet per second, or if I liked, 44.1 miles per hour. Now, it's important to note that this is the rated speed if we were only going to say, if we were designing it only for, if we were designing or relying on only the normal force to produce any kind of turning force or any kind of centripetal force. So, in other words, this is kind of the worst case scenario. This is kind of the scenario of if I was driving on ice or something like that, or even something higher, like Teflon coated roads or something. Yeah, there's no friction at all. In reality, we left out friction to make the analysis a lot simpler, but in reality, that friction is going to be quite substantial. And so, but if you think about it though, what this does is that it makes it a lot easier for the for a car to go around a curve. And a car, your tires have finite frictional capacity, don't they? They have a finite frictional capacity. And so they have a finite frictional capacity. They can only carry so much frictional force. And it's actually based on your weight. So the more weight they have, you don't actually get more for adding more weight, because yes, you have, you don't actually get more for adding more weight, because if you make your car heavier, yes, the frictional force increases, but in turn, the amount of frictional force you need to accelerate, stop, or turn will go up in proportion. So you don't actually get anything out of having a heavier car in terms of friction. At least in terms of very simple turning radiuses. There can be other benefits for like snow and things like that, but that's something different. Okay, so what are some implications of this? Well, what did you notice in regards to the mass of the vehicle, the weight of the vehicle? What happened to it? What happened to the weight of the vehicle? It cancels. It's irrelevant, yes. Because what would it look like if this didn't work this way? What would it look like if the mass of the vehicle did not cancel out? What you would need is, when you actually designed highways, you would have to have some crazy system where you all came, every time you wanted the road to turn, you'd have to do some crazy thing like this, where you'd have the road coming in together, and then maybe it would like split off into two or three pieces, and maybe the compact cars go here, maybe the big pickup trucks go on this road, and the big 18-wheelers go on this road. Just roads of different curvature, of different radii, and then they sort of straighten out, and then they'd have to like merge back in together. They'd have to merge back together after the turn. That would make highway design very difficult, wouldn't it?
Or they could just have a bunch of separate signs saying what speed you had to go on your weight.
Yes, you could do that. You could just have a bunch of separate signs indicating what speed people would have to go. But then, if the road was viable for small passenger cars traveling at 60, 70 miles an hour, that would mean your trucks would probably have to slow down to 20 miles an hour or something. Well, depending on, well, I can't speculate on how the math would work, because I'm basically imagining a world with alternate physics, so who knows how that would work. But anyway, so that would be kind of weird. Now, this also produces an interesting limitation here. So V squared equals rho g tan phi, right, for a banked curve. And this is the maximum velocity you can travel around on the surface of a highway for relying only on frictional force. Well, there's an interesting issue at that here. Huh? Oh, sorry, relying only on normal force. Sorry, not relying on frictional force. Well, let me think of something else. I basically have a few topics I want to discuss on this. Theta. What happens as theta goes to 90? Now, I'm going to pull up some pre-cal, so I'm hopefully not going to give you horrific flashbacks to pre-cal. But if you remember your pre-cal, if this is theta and this is tan theta, right? There is actually asymptotes on the tangent graph at pi over 2, negative pi over 2, and this repeats every pi cycles. Negative pi over 2, so it actually behaves kind of like this. And you said that, and you thought your trig would never have applications. Well, here it is. See, if as tan approaches 90 degrees, the allowable velocity, basically the limit of v as theta approaches 90 degrees is infinity. So, of course, at that point, you have just a vertical wall that your car is just spinning around at incredible velocities. Oh, actually, that's another thing, though. That's another interesting thing. Could you ever actually drive around a purely horizontal wall?
Yeah. Don't those motorcycles do it at the circus?
Well, let me think about actually a purely horizontal. Let me think about that. Could you ever actually drive around a purely horizontal wall? Well, I guess it might be. Well, let me think about that because. Well, I'm thinking about is well, there might be frictional force. Actually, I suppose you could if you're going fast enough. This wasn't really created as this calculation wasn't a minimum speed to go around to travel the road. It was this calculation wasn't based on a minimum speed to stay in the curvature. It's the maximum allowable speed. So, but yes, if you had it, so right at here, you could effectively have infinite speed. That doesn't mean you actually can go infinitely fast. This just means that on a purely horizontal wall, if you just had a horizontal track, and you just had, just a car going around it sideways, you'd have to be going rather fast to do that. But I suppose it could if you really wanted to. If you went fast enough, it would just go around and around and around and around and around. Kind of like those motorcyclists you see at the circus sometimes. Other things, what can you tell me about constructing highways on the surface of Mars? There's a great conceptual question. Think about that for a second. Constructing highways on the surface of Mars.
Is it something they have the oxygen to run?
Well, let's not. They could be electric cars. The question is, what about highways? There's no oxygen on Mars. How are the engines run? Well, they're electric moon buggies. I don't know, something like that. So let's say I want to build a highway on the surface of the moon or the surface of Mars. What's the problem with that? Well, if I look at the required radius of curvature, it's going to be v squared divided by g tan of phi. So, in other words, if I'm on a planet or a body with, let's say I'm on the surface of the moon, where the acceleration due to gravity is 1/6 that of the Earth. So that means my radius of curvature is going to need to be 6 times what it would need to be on the surface of the Earth to make it through a banked curve. So if we ever do build highways on the moon, well,
For that moon tourism.
For all that moon tourism, you might go to see the whalers or something like that. You never know. That's really whalers on the moon. Oh, never mind. Okay, so that's the basic idea. Good. So I just wanted to walk through another example, really here, of finding, of setting up free body diagrams, inertial diagrams, and working through the relative implications of it. So, this here. Okay, so let's look something else. I want to move on to a new topic, and that is the equations of motion using radial and transverse coordinates. So equations of motion in radial and transverse coordinates. in radial and transverse coordinates, or components, I should say, and transverse components. Components. Okay, so previously I've been looking mainly at rectangular components for my equation of motion, but I would like to now look at essentially polar coordinates, because there are definitely cases where it's beneficial to work with polar coordinates rather than rectangular components. So consider a particle at r. Well, that is really bad. Consider a particle at r and theta at r and theta in polar coordinates. Oh, and theta, or in other words, in polar coordinates. So here, I'm going to have something like this. Oh, something like this here. If I look at the summation of forces, I can basically, just like I did in the case of rectangular components, I can also set up equations of motion in polar coordinates. So, and I can do the same. We will do the same sort of inertial diagram and rectangular diagram, or sorry, inertial diagram and force diagram system that we've used before. So I could use the summation of forces in the radial direction is equal to m, acceleration in the radial direction, MAR, and this will be equal to m r double dot minus r theta dot squared. So they essentially, for our polar coordinates, the acceleration in the r direction will be equal to r double dot minus r dot theta dot squared. And then the sum of forces in the theta direction, or the angular direction, is going to be m a theta, a sub theta, the acceleration in the angular direction, is going to be equal to m r theta double dot plus 2r theta dot, or 2r dot theta dot. And there is no r dot here. This is the only component. So this is r double dot, r theta dot, r theta double dot, r dot theta dot. Simple, right? It's just a piece of cake. It's just a dot here, or there. Just simple, right? I know this can be tricky. You'll get through it. Okay. So here, I'm going to draw a couple diagrams, again with paths in purple because I seem to like doing that. Oh, that's not purple. So say I had a path here, then another path here, same kind of thing. It's meant to be the same path. So let's say the origin is here for this one. One of these is going to be a force diagram, and one of these is going to be an inertial diagram. So I would have, let's say I have a particle, same position, r and r.
The inertial diagram, is that similar to the kinetic? That's the same thing as the kinetic diagram?
Yes, when I say kinetic diagram, I mean inertial diagram, inertial force diagram, kinetic diagram, same thing. No problem. P here, P here. So I have a particle P here, and it's going to have mass m and mass m, and it would have radius r and r in each case. So it'll have two coordinates, r and theta. R and theta. R and theta. So these are its coordinates. And the force, it will have forces acting on it in two directions. Instead of looking at x and y, I'm going to look at the summation of forces in the radial direction, the summation of forces in the radial direction, and the summation of forces in the angular direction. Summation of forces in the theta direction, or the tangential direction, or transverse direction. So, in basically, probably the best way to say this would be radial and transverse direction. Okay, and then this would be equivalent to the M AR and MA theta. MA theta. So, acceleration in the theta direction, A sub theta. It's important to realize we're not talking about an angular acceleration here. We're just talking about a linear acceleration, but in the angular direction. See, look, MA theta. Look at the units here. If I work through this would be meters, and then seconds to the -2, right? So this would be meters per second squared, if I'm doing metric units. And this would be meters per second, right, times 1/2. So meters per second square again. So meters per second square again. So we can see here that it's important. I just want you to be very careful not to confuse theta double dot with A theta. So let me actually go and expand on this a little bit. Here, A theta is not equal to theta double dot, okay? Or AR is not equal to R double dot. Here is not equal to R double dot. So here, to R double dot. Otherwise, you'd have something where, in the previous equation, where it's equal to itself. R double dot is just going to be the, for example, it's easiest to explain on this one. A theta is just the component of acceleration pointing towards center. Towards center. Towards the center. And, but theta double dot, and so this would be units of something like, if it could be meters per second squared, but really dimension-wise, it's length time to the -2. Theta double dot, on the other hand, is your actual rate of angular acceleration, or your actual angular acceleration. This would be in something like radians per second squared, or dimensions of simply time to the -2. Simply time to the -2. AR is the acceleration component. Oh, actually, sorry, not pointing towards center, sorry, pointing, I should say, transverse to radius. Transverse to radius. And acceleration here, pointing towards center of curvature. And R double dot would be the actual rate of change, the actual rate of change, or this relates to the rate of change of the radius itself.
Pointing towards the center of curvature or along?
Pointing towards the center of curvature. So if you have an arc, the center of curvature will be here. So it's going to be, AR is going to be pointing toward the center of curvature. Well, actually, no, it could be pointing, you're right. It could actually be along the center of curvature. It could be towards or away, depending on how you define it. You're right there. Because in my previous diagram, I have it pointing away from the center of curvature. So I should say along the center of curvature, you're right. Relates to change in the radius itself. In the size of the radius itself. I've been trying to think of a clear way that distinguishes between these, and that's the best way I can describe it, of the radius itself. So that's talking specifically about how fast the object's path radius is changing. This could be just the, this could be actually the, okay, so let me give you an example here. What is the difference between AR and R double dot? Let's take a look at this. So AR versus R double dot. Let's think about this. If I consider, the best example I can think of to illustrate the difference of these is consider uniform circular motion. Circular motion. Consider uniform circular motion. I have a particle here, and this would be going, there would be an R here, there'd be an R like there, and my AR would have to point in the radial direction, right? This is what's going to produce the acceleration, the centripetal acceleration. If this thing has a velocity out like this, so it would have a velocity here like this, a tangential velocity like this, and there needs to be something to produce this, there needs to be some acceleration to produce that. In fact, maybe I'll show it like this here, so these aren't overlapping. Actually, let me just go ahead and move this over here, so they're not on top of each other. So there's an R. Let's say this is a uniform circular motion problem, and there would be a AR here, and some sort of, if this was actually accelerating, there could be a theta here. However, in uniform circular motion, a theta may be 0. In other words, it's not accelerating in the transverse direction. It just, especially if, example, if rotating at a constant rate. At a constant rate, it would have angular velocity, but not angular acceleration. However, in uniform circular motion, this would still have a centripetal or a radial acceleration. See, the centripetal acceleration in this case, AR, would have to be equal to m. Actually, I've been using rho, so let me be consistent. M v squared over rho, would it not? If we remember from physics, our centripetal acceleration formula, mv squared over r. So this is the acceleration the object is experiencing to cause it to travel in a circle. It's just traveling at a constant velocity in a circle. This could be something like a circular orbit. It'd just be going in circles all day long, day after day, endlessly, just repeating its infinite path. But the question here is, I just told you that AR is this. What is R double dot? What do you think R double dot is? In this case, R double dot would be null, nothing, 0. Why? Because the radius is constant, yes. See, at first glance it might seem, wait, why is R double dot and AR different things? And the reason is because R double dot is talking specifically about how big the radius is. So if this thing is going in a circle, there still needs to be some acceleration on the object pointing toward the center of the circle, but the radius itself is not going undergoing any change. An example where there might be some sort of circular motion or quasi-circular motion with a R double dot not equal to 0 would be something like this. Imagine you have, say, a decaying orbit. Consider a decaying orbit. So for very high satellites, this is not a significant factor, but for something something in low Earth orbit, like the International Space Station, orbits decay. You see, we say that space is a vacuum, but it's not. There are small traces of atmosphere that can slow things down. The International Space Station experiences drag. Now, if you're in high Earth orbit, even those would experience drag, but even something like the moon experiences drag around the Earth. But if you compare the volume of the moon relative to its surface area, its volume and mass are so incredibly large relative to its relatively tiny surface area that drag is effectively zero on it. It will happily keep orbiting the Earth until long after the sun has grown cold and dead, before the tiny amount of friction in the tiny particles around the Earth's orbit would ever cause a decay of the moon's orbit. In fact, it's actually moving away from the Earth right now. But anyway, but for something in very low Earth orbit, it's going to experience substantial drag. Now, that doesn't mean that it will fall out of the sky relatively quickly. It's nothing like the drag a plane would experience, or the drag a car traveling at sea level would experience, or something. So you can't, go outside at the space station and take your helmet off. That would be rather bad for the sake of biology. We can treat the space around in low Earth orbit as a vacuum. But for spaceship design, if you're counting on an orbit that will keep you up there for years and years and years and years, it is not a perfect vacuum. And so what they have to do on the space station is all of the supply rockets that fly up and attach to them, bring more supplies. Often they'll use those to, if they have a little extra fuel in their tanks, they'll use it to sort of boost the station's orbit. They have to do what's called station keeping, where they boost the station's orbit periodically in order to cancel out the effect of drag. And so, but let's say they didn't do that, or let's say you just had an old satellite that's slowly coming down. And so it starts out here, and it wouldn't do this over one orbit. This would actually be over many, many, many orbits. I'm going to try to draw this decently well. So it wouldn't actually spiral this tightly. It would take many, 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 many orbits. But it would eventually do something like that. And let me draw the Earth in blue here. This is the Earth. Or any planet. Could be Neptune. I don't know why I'm spending so much time to color this all the way in. Just because I feel like a third grader. Coloring inside the lines. Actually, that's more like first grade or kindergarten, isn't it? Anyway, that's okay. So we have our planet here. Nice, pretty blue marble. I don't know where all the land went. That's kind of scary. But anyway, so this spaceship or satellite or whatever it is on a decaying orbit. And so if we look at this decaying orbit here, well, theta dot is not equal to 0, right? Theta dot is not equal to 0 because there is a rate of an angular velocity. Tangential velocity is not equal to 0. Sorry, is not equal to 0. Acceleration in the r direction cannot be equal to 0 because this thing still has to travel in a circle. Acceleration in the theta direction or the transverse direction cannot be equal to 0 because it's experiencing drag that's causing it to slow down. And here, though, in this case, r double dot would also not be equal to 0 because this is a decaying orbit. The rate of change, the radius is decreasing. If the radius is decreasing, there must be some sort of r double dot. Now, this r double dot would be incredibly small. We're not talking something that happens quickly. We're talking about a process that takes years on a low Earth orbit. They might go around the entire planet in something like, 40 minutes? Is that right? 40 minutes, something like that? I think that's about right. Maybe I'm wrong there, but I think it's only about 40 minutes to go around the entire planet in low Earth orbit. So they're trucking along there pretty quickly. And so if you think about it, if it takes years, this is not accurate at all. In reality, it would be something like thousands and thousands and thousands of circles, something I couldn't possibly hope to draw out on any realistic scale. But this would be one example I can think of that clearly indicates a case where r double dot is not 0 and ar is also not 0. Okay, so let's work through I want to work through an example problem. All right, so how are we doing time-wise? We're doing all right. I think I'll work through an example problem and then maybe I'll let y'all take a break. Sound good? Okay. And we'll come back for part dos. Okay, so let's say I have something like this. I have a example again. A block B of mass M, can slide freely on a frictionless rod, frictionless arm OA. And I will draw this. OA, which rotates in a horizontal plane, which rotates about, or I should just say rotates at a constant rate, O theta dot O. Or theta dot O. Okay, so let's draw this out. I have a pin support here, which is going to allow rotation. And then I have a rod hanging from this, or supported by it, etc. And this thing is rotating. And so basically, let me draw this out a bit more. And then over here at A, there's a cap that will prevent the object from coming off, the collar from coming off. And then there's going to be a collar here along this thing that at any given location is, at any given time, is going to be a radius R from the center. So this is the R that we're looking at, R. And I'm going to say that VR is going to point in this direction, VR. It's going to be positive VR. And then, so as this thing rotates, this thing's going to move upward, or be flung outward. And this will be my theta, my measure of angle at any given time. And also I can say that theta dot is rotating, it's rotating this way. So all of this is given. Theta dot is simply going to be a constant, theta dot A. So this is rigid rod, it's rotating at a certain rate of angular, at a certain angular velocity in radians per second, and this thing is moving there. So all this is given, and I want to find also, actually, let me state this. Here, actually, this is going to be block B, sorry. This is block B. And another statement is that block B is released a distance R naught from O. A distance R naught from O. Okay? And I want to know this. I'm asked to find, as an expression of R, A, the component of V, the component VR, the radial component, how fast it is sliding along the shaft here, of the velocity B along OA, the velocity B of the block B, let's say of the velocity of B along the rod along OA. So this is point O and this is point A. Okay. And then B, I want to find the magnitude of the horizontal force exerted on B by arm OA. Exerted on B by OA. All right, let's continue and work through that. So I'm going to just draw out the same kind of thing here. Now it's interesting that they're the same kind of force and kinetic diagrams I had before. Now what's interesting about this is that if we think through this, that this collar, because it can slide up and down, this arm can only exert a force this direction. It cannot exert a force like this. It can only exert a force like this on the collar. And I'm going to go ahead and neglect the mass of the, or the weight of the collar for our case here, for our simple cases here. I'm asking how the collar affects the, how the rod's motion affects the collar. I'm not actually asking for its overall motion, so that's why I'm going to be able to neglect the weight of the collar. I'm only looking for how the rod's motion affects the collar. Oh, yes, you're right. Actually, sorry about that. Yes, it's rotating in the horizontal direction. That's why that's the real reason I can neglect it. Sorry about that. It's rotating in the horizontal direction. So I'm going to have a block here, O here, and this is at a certain theta initially, or actually at any given time it's at a certain theta. And then I have the force F that will be exerted by the rod on the collar. And this in turns, this is my only force diagram on here. This is the only force on my force diagram. This must be equal to the inertial diagram, which will be, or the kinetic diagram, which will be MAR and MA theta, the radial and transverse components. Okay, so I want to first, let's see, I want to write the radial and transverse equations for the motion of the block. So first step, let's see, will be to write the equations here. So well actually the first step would be the diagrams, but anyway, after that, write the, let's see, the radial and transverse equations, and transverse equations, equations for the motion of the block, so the summation of forces in the R direction is going to be equal to, well, let's see, in the R direction, if I do this, well, there is no force in the R direction, so it's just going to be 0 equals MAR, which, as we saw earlier, is equal to M times R double dot minus R theta dot squared. And then I know also that, so this is based off of, actually, let me just say this is based off of MAR, and the summation of forces in the theta direction, the transverse direction, is equal to MA theta, which is then equal to F, the force F here, F equals M R theta double dot plus 2R double dot theta dot. Okay, so that's the first step. And then going along, I want to integrate the radial equation to find expression for the radial velocity. Let's integrate the radial expression to find equation, let me integrate the radial equation to find the expression of radial velocity. And I'll do that on the next slide. So if I start out again with here, the radial equation, well, I know that r double dot is equal to dvr dt is equal to, if I put in a dr in here, dvr dr times dr dt, or vr times dvr over dr here. So there you have it. The change in radius is going to be equal to the acceleration. No, I keep saying acceleration. Sorry about that. The rate of change of the radius is going to, or just the r double dot, is going to be equal to the velocity in the radial direction times the rate of change in the velocity in the r direction.
How do you get the original portion of that?
The original portion of that here, this one,
Yeah, like it says that VR equals R dot. Where did that come from?
VR dot, VR, yeah, this is equal to VR dot,
That was right, but
r double dot, yes, VR dot.
it says since VR equals R dot, you have, and then it has that equation. So I was just wondering where they got
In this equation, well, actually, in this case, because just in this particular case, the rate of change in angular velocity will be equal to the rate of change in the radius. Yes.
Okay.
In this case, that's what would it.
Like intuitive.
Yeah, this is intuitive. It's coming directly from this. In the case of like a uniform circular orbit, this wouldn't be the case, but in this particular case, that's where it's coming from. Okay, and then I can say r double dot equals VR double dot equals dVR dt equals dVR, isn't this fun, over dr, let's see, dVR dt over, and I'm just doing a conversion of variables again, over dr times dr dt, dr over dt equals VR dVR over dt. Over dr. And then I can plug and chug, setting one of these equal to another, etc., etc. I can say VR dVR dVR equals r theta double dot squared times dr equals r theta naught squared dr. Or if I then go to integrate this, if I integrate this from 0 to VR, and maybe this one here, let's integrate, actually I think I'll integrate this one, I'll integrate this one here, where theta double dot can be, let's say theta, there's a dot here, sorry, theta dot can be pulled out, so integral 0 to VR of VR dVR equals theta naught dot integral of r dr, and evaluated from r naught to r, the initial radius to the final radius. And so VR squared is going to be equal to theta naught squared, and I can pull that out because it's going to be constant. Theta naught squared, that would be the initial position, not the initial, that would be the initial angular position, times r squared minus r theta squared. And then if I substitute back in known quantities into the transverse equation to find the express, so finally I can take this and substitute into the other equation, and I can get that F is equal to 2m theta naught squared times r squared minus r naught squared to the 1/2 power, or just the square root of all of that. Actually, I won't do that. Let me just put a big old box around all of this. This, and my other result is this here. Basically, I need to plug this into the earlier force expression we had, let's see, here, I suppose. Okay. Or actually, where does the force F, no, here, this one here. We'll need to plug that idea of VR here into some of the other equations, resolve, etc. But you'll get F equals 2 m theta. Again, the way you get that is to substitute the known information to the transverse equation to find an expression for the force on the block. And if you did that, work through some of the algebra, that's what you'll get for the force expression. All right, I think that'll do it for part 1 here. Let's take a short break, come back, and we will look at some new material, including conservation of momentum.